Why is manufacturing a 3-nanometer chip so hard? It has been described as a near-death experience for any company that attempts it. So, why do we do it? The earliest chips were crude. You could see the circuits with your naked eye, and they were simple enough to be soldered by hand. But to increase computing power, the number of circuits had to increase exponentially. The problem was that massive amounts of electricity were being wasted as heat. To lower power consumption, we had to shrink the circuits. Over the last few decades, circuits went from the millimeter scale down to the nanometer scale. Today, they are far smaller than a speck of dust. A single modern chip can carry over 50 billion transistors, creating a massive leap in computing efficiency. But these circuits aren't just thin, they are stacked in many layers. Like a microscopic city. You cannot build this with any mechanical tool. Instead, engineers decided to use light and chemical reagents to carve it out, layer by layer, like building a skyscraper from the ground up. Light is responsible for transferring the blueprint onto the silicon wafer, while chemicals are responsible for carving out the circuit design. Here is how it works. First, a thin layer of photoresist is coated onto the wafer and baked to soften it. This material is sensitive to ultraviolet light. When exposed, it hardens or changes properties. We then shine UV light through a photomask which acts like a stencil. The parts of the wafer blocked by the mask remain unchanged, while the exposed areas react to the light. When washed, the exposed photoresist dissolves away, leaving the shape of the mask behind. We then use chemical solutions or plasma gas to etch the wafer, removing the parts not protected by the photoresist. This leaves behind the circuit pattern, just like using a stamp. Low-precision lithography machines can handle processes above 28 nanometers. However, at the microscopic scale, light begins to diffract and scatter. The finer the circuit, the shorter the wavelength of light you need. To challenge the 7-nanometer barrier and go lower, we needed a type of light that doesn't exist naturally on Earth, extreme ultraviolet, or EUV. This relies on the EUV lithography machine. The process is insane. First, a generator shoots a microscopic droplet of molten tin. While the droplet is flying through the air, it is hit by 2 separate laser pulses. The first laser flattens the droplet. The second, high-energy laser hits it again, vaporizing it into plasma and releasing extreme ultraviolet light. This light is then reflected by a set of atomic-level molybdenum silicon mirrors onto the photomask to expose the wafer. This sequence happens 50,000 times every single second. After exposure and etching, we have to wire up the building. Silicon is a tetravalent element. When we inject it with 5 valence ions, electrons easily flow out. Inject it with 3 valence ions, and electrons are attracted. This allows us to control the current, creating the on and off states, the 1 second and 0 second that form the basis of all calculation. Next comes the polishing. We use ceramic particles smaller than a micron to polish the wafer while constantly washing it with abrasive liquid. The difficulty of this polishing is equivalent to building a railway from Shanghai to Beijing where the ground height difference cannot exceed 1 millimeter. Only after this perfect polishing can the next layer of the skyscraper be built. Coating, exposing, etching, depositing, and polishing. This cycle is repeated over 100 times. Finally, copper and other precious metals are added to create the elevators connecting the layers of this microscopic city. The entire process involves over 1,000 steps and takes 3 months to finish, because every step requires rinsing with ultra-pure water. A single fab can consume 8,000 to 10,000 tons of water a day. This water must be highly purified to prevent even the tiniest impurities from ruining the chip. Producing just the single processor inside your phone requires an estimated 32 kilograms of water. Additionally, high-temperature ovens must run 24/7, and the air needs to be constantly circulated to remove dust, requiring a massive power supply. Beyond water and electricity, the process consumes huge amounts of acid, alkali, gases, and precious metals. This is why chips, especially high-end ones, are incredibly expensive. A single high-end NVIDIA chip can sell for tens of thousands of dollars, and TSMC invested over $20 billion just to develop the 3-nanometer process. Building a chip isn't just a near-death experience for a business, it requires the support of an entire global industrial chain and the full weight of modern society. Without this powerful production network, It would be impossible.